Welcome back. In this video, we're going to discuss how to take the integral of functions or expressions which take this form right here. Either a squared plus x squared, or a squared minus x squared, or x squared minus a squared. And if you're very perceptive, what you'll notice is that this takes a form of a standard integral that you may have memorized, which is either arctangent, arcsine, or something along those lines. You may think, I can just look at this and, rewrite it as, because this is just a standard integral, as arcsine of x over 4. And you wouldn't be wrong, but it's not good necessarily as you enter much more complex integration for you to just brute force memorize these forms, but to understand how they were determined in the first place. Because if you can understand how they were determined, right, if you get a more complex expression, which looks maybe something like if you understand first off how this expression was integrated to arcsine, you can use the same exact techniques to determine what the integral of this complex expression might be. I want you to try and follow along to understand how they came about that arcsine, or how the techniques that can be used to integrate an expression like this. And it starts with an understanding of the right triangle and basic Pythagorean identities, right? So what I've drawn here is just a basic right triangle, and I have my Pythagorean identities of a squared plus b squared equals c squared. And if you're an even more perceptive mathematician, you may recognize that this 16 minus x right here, right, it is the same thing as 4 squared minus x squared. And that looks just like the form c squared minus b squared equals a squared, right? And this is just a rearrangement of Pythagorean's identity. All I did was I brought my b squared to the other side. But that means that I can interpret this expression underneath the radical in terms of a right triangle, right? I can rewrite this right triangle with my c equal to 4, my b equal to x, and my a equal to the square root of 16 minus x squared. And the reason why we're kind of going through this as trigonometric identities here, or in terms of a right triangle, is because of the power of trigonometric identities, right? And the main motivation, which you'll understand after watching this example, is that we can rewrite this radical in the denominator as the product of two squares, a squared and b squared. And that will allow us to get rid of that radical and to find some product a times b, which will help us simplify our expression. And so I'm just going to continue with my example, and I hope that you follow along here. But we've just rewritten this triangle with our hypotenuse being 4, our b being x, and our a being the square root of 16 minus x squared. And if you look very closely, you can see I did this. All I did was I rearranged Pythagorean's identity, right? And then I interpreted this as this goes to 16, right? So the 4 squared is just going to be 16, and that's going to be my x for b, right? B is just going to be x. And my a squared is equal to the square root of 16 minus x squared, right? And so now I can kind of interpret this whole denominator under the radical, that part under the radical, as some triangle. And this comes in handy, and you'll see why here. We can do this very tricky and convenient substitution, which will allow us to convert this part under the radical into the product of two squares. This x is just equal to 4 sine theta. And how did we get that? We chose this angle right here, and we know that the sine of that angle is going to be equal to the opposite over the adjacent, which means if we wanted to isolate our x, get our x alone, we'll find that it's equal to 4 sine theta. And so now we can perform this kind of substitution with our integral, and I'm just going to rewrite this substitution. But now we have an issue, and that issue is that our integral is integrating with respect to x, and we have just subbed in a theta. So now we need to have some type of way to get rid of our dx. And our dx, right, the derivative of x with respect to theta, is just going to be 4 cosine theta, right? And you can verify this for yourself. You can try and find what the derivative of x is, and you'll find that it's going to be 4 cosine theta, but that d theta, sorry. But that now allows us to write our integral expression in terms of theta. Now, remember, the whole motivation in doing this long process and trying to interpret the expression underneath our radical in terms of the Pythagorean triangle was just so we could rewrite the expression under the radical as the product of two squares. And you'll see how we come about that really soon. Let's just focus on the part underneath our radical, right? This 16 minus 4 sine theta squared, right? We're just going to focus on this part and we're going to simplify it. So first we're going to square this expression right here. We're going to find that that's equal to 16 minus 16 sine squared theta, right? And then what we're going to do is we're going to draw a 16 out. 16 times 1 minus sine squared theta, right? And if you want to check for yourself, you can say if we distribute that 16, and then we're going to get 16 minus 16 times sine squared theta. And we know, according to the trigonometric Pythagorean identity, that 1 minus sine squared theta is just cosine squared theta. So we're going to get 16 cosine squared theta as our new expression underneath the radical, which means that we can rewrite this whole expression right here as the integral. And according to this principle right here, which tells us that the square root of the product of two squares is just the product, the absolute value of the product of those two numbers. And that means, and this was kind of our whole motivation of, rewriting this expression underneath the radical in terms of the triangle, was to be able to express that difference as a product. And this is a very powerful tool, and you'll see why here right now. Because I can now rewrite my integral as just 4 cosine theta, right, over 4 cosine theta, d theta, right? All we did here was we said, okay, 16 is 4 squared, so our 4 is our a, and cosine squared theta is our b is just going to be cosine, and so the square root of 16 cosine squared theta is just 4 times cosine. That's all we got here. And now this can be rewritten as the integral of 1 d theta, whose integral is going to be theta. And we've almost solved our integral here, right? But all we did was we found our integral in terms of theta. Now we need to try and get it in terms of x, because that was the original point of our equation, right? And we know that x equals 4 sine theta, so we can say x divided by 4 equals sine theta, and then we can find the inverse sign, or the arc sign, right? So the arc sign of x over 4 is going to equal theta. And now we can sub in our arc sign of x over 4 for our theta, right? And we can get that our final integral is just going to be arc sign of x over 4 plus c, right? That's our final integral. And so all we really did here was we as a kind of recap of what we've just done, we could try and use our trigonometric identities over here to reinterpret it as the product of two squares. And then we were able to simplify that integral and take the integral with respect to theta and then sub back in our function right here. Now I'm just going to do another example to show you the power of this technique. We're going to go 1 over, right, 16 minus x squared to the 3/2. And again, it's more about the process and kind of trying to intuitively understand that process. But the reason why I show you this is it's very similar to the last one, right? But this can be written as the square root of 16 minus x squared cubed. And if you were to approach this problem initially, you couldn't say arc sine of x over 4 because you have this cubed right here. And so this is where our understanding of the integration, right, understanding how these rules came about, helps us to solve this problem. We just focus on the portion under the radical. So if that portion takes the form of a squared plus x squared, or a squared minus x squared, or x squared minus a squared, right, we can use our trigonometric identities and we can interpret that portion under the radical in terms of a right triangle and find a very convenient substitution. So we're going to do that right now. So this form right here, just like last time, it looks similar to c squared minus b squared equals a squared, which means that our c is just going to be 4, and our b is just going to be x, and our a is going to be the square root of 4 squared minus x squared. And we can draw that into our triangle right here. So I'm going to put my x right here and my 4 right here and the square root of 16 minus x squared here, right? And we can substitute in an x right here. that would be very convenient. And it's exact same as last time. That x equals sine theta times 4. And my dx, right, because in our expression over here, which I keep forgetting to draw, we have a dx and we have to get rid of it if we're going to integrate with respect to theta. My dx is just going to be 4 cosine theta d theta. So now I can draw my integral as 4 cosine theta, right, d theta over 16 minus 16 sine squared theta to the 3/2 power. And all I did here was I subbed in my x, right, and I got 16 sine squared. And now I'm going to draw that 16 out and try and interpret that part in the denominator as the product of two squares. And so we're going to get, which is just going to be equal to the integral of, and now I'm going to distribute this 3/2 into my expression right here. And this is a slight deviation from this, right? But you can think about it intuitively. So 16 to the 3/2 is just going to be 64. So we're going to say that this is just going to be equal to the integral of 4 cosine theta, right, over 64. So that 16 to the 3/2 is going to be 64. And then cosine squared to the 3/2, right? You just draw this down here. Cosine squared to the 3/2 is going to be equal to cosine to the 2 times 3/2 theta, which is, those twos are going to cancel out, and we're going to get cosine cubed theta, right? So our denominator is going to be 64 cosine cubed theta d theta. And we're almost there, right? All we have to do is kind of simplify our expression. And so we're going to say that one of these cosines cancels out with one of these 3 cosines, so we're going to get cosine squared theta. And 4 over 64 is just 1 over 16. So we're going to rewrite this integral down here as the integral of, that can also be rewritten as 1/16 the integral of 1 over cosine squared theta d theta, right? All I did was I took out my 1/16, and that's just 1/16 the integral of secant squared theta d theta. And we know this secant squared is just a standard integral, and that's going to be tangent of theta over 16. And now we have to try and sub back in for in terms of x. So we go back up to our triangle up here, and we see that the tangent of theta over 16 is our final integral. But in order to sub back in for x, we have to rewrite this tangent theta in terms of, right, the opposite over the adjacent, right? So this expression can be rewritten as, all I did was I took my final integral in terms of theta and I rewrote it in terms of x. And I just went back and referenced my triangle up here. So the tangent of theta, right, the tangent of this theta is going to be equal to the opposite, or x, over the adjacent, which is square root 16 minus x squared. And then I can rewrite this final integral as x over 16 square root 16 minus x squared plus c. And that's my final integral for this example. So you can see that through the same process by which we found the integral, the last problem that we just did where we found that the integral was arc sine of x over 4, that with the exact same process we can find this more complex integral. And we find that arc sine was not involved in this at all, and that it's actually this more complex function right here. So now we're just going to talk about the two other forms, right? So I mentioned that if you have some integral of 1 over the square root of, a squared plus x squared, that you can have different forms under this radical. You may have a squared plus x squared, or a squared minus x squared, or x squared minus a squared. And each one of these is going to utilize its own unique substitution or own unique technique. It comes down to only 3 substitutions. You're either going to do a tangent, a secant, or a sine substitution. And the last 2 problems that we did fit this bill right here, this middle one. And so we did a sine substitution. If we look at this form of a squared minus x squared, and let's make it 16 minus x squared, right? Just like we did in our last problem. we can analogize this 16 minus x squared with our Pythagorean theorem to c squared minus b squared equals a squared, right? Or 4 squared minus x squared equals the square root of 16 minus x squared. And we can make our a, b, and c be the different parts of this expression under the radical. And assuming my theta is oriented right here, I'm going to have to take the sine of that theta in order to get this in terms of x. But what substitutions will we use if the expression underneath our radical is a little bit different, such as a squared plus x squared or x squared minus a squared? And let's just start with this one right here. So if it's a squared plus x squared, right, instead of a squared minus x squared like we've done for the last two problems, we're going to get 16 plus x squared. And this form is analogous to a squared plus b squared equals c squared, right? So I can make my a 4, I can make my b x, and I can make my c be the square root of 4 squared plus x squared. So now if I wanted to get my x in terms of something convenient, if I were to use sine, I would get x is equal to sine of theta times this complex expression right here. And we want to make this as simple as possible. So the most convenient expression to use would be tangent. Tangent of theta, right, will be equal to the opposite over the adjacent, or x over 4, which means that my x is going to be equal to 4 tangent theta. Okay? So I'd use this substitution because this is the most convenient. Now the final one, right, because we just determined that if we have a squared plus x squared, the most convenient substitution, right, would be a tangent substitution. And for this one, it would be a sine substitution. But for this one, right, the most convenient substitution for x squared minus a squared, right, which we'll do our 16 here, would be a secant. And how do we get that? So this x squared minus a squared is analogous to c squared minus a squared equals b squared. So we're going to sub in our x right here. So we're going to get x squared minus 4 squared, right, equals the square root of x squared minus 4 squared. And so our b is going to be x squared minus 4 squared, right, because b squared, if we make b squared equal to x squared minus 4 squared, then b is just going to be equal to square root of x squared minus 4 squared, right? So I guess you can put that as a square. But that means that our b is going to be x squared minus 4 squared, and then our a down here is just going to be 4, and our x is going to be our hypotenuse. So in order to do a trigonometric substitution, we need to get x in terms of our simplest other portion, which is going to be our 4, times some trigonometric function, some trig function, right? Trig of theta. And that trig of theta, that convenient trig substitution, is just going to be x over 4. And x is our hypotenuse, and 4 is our adjacent, according to this theta. And the only trigonometric function where the trig of some angle is equal to the hypotenuse over the adjacent is secant. So the most convenient trig substitution here will be of secant. So we're going to get 4 secant theta, right? And you can do the exact same process as we did with the first two problems, where you try and plug in a secant or a tangent or so and find the integral there, and that would work the exact same way. So we're going to do one example. We're going to choose tan right now. Okay, so let's say we have some integral 1 over 1 plus x squared squared dx, right? So this might not immediately stand out to you because you're so used to seeing stuff like square roots or to half powers, but you can use a trigonometric substitution even if you have a power rather than a root, right? So the substitution that we would use here, because it takes the form of a squared plus x squared, is a substitution of x is equal to a tan theta, right? And how do we get that? The reason why we interpret the triangle this way is because it kind of takes the form of a squared plus b squared equals c squared, right? The Pythagorean identity, and all we did was we interpreted this portion under the radical, or under that squared, in terms of Pythagorean's identity and subbed it into our triangle, which means our a is going to be equal to 1, because we'll get 1 squared plus x squared equals c squared, and that's going to be our c, so we can sub in a 1 right here. And we determined, right, that the most convenient substitution for this form is going to be equal to, is going to be a tangent substitution, right? So x is equal to 1 tan theta, and you can verify this for yourself, right? If we have our arbitrary angle right here, this theta right here, then the tangent of theta is going to be equal to my opposite over my adjacent, which is just 1. And therefore, if I rearrange this, right, I'm going to get x is equal to tan theta. So now we will sub in our tan theta, right? We're going to get 1 over 1 plus tangent squared theta squared dx, right? Where do we get this tangent squared theta? Well, we said our x was equal to 1 tan theta, and if we sub in our 1 tan theta right here and we distribute that squared, we're just going to get 1 plus tangent squared theta squared, right? This is our expression. But we can't integrate this expression because we have a dx, and we want to integrate in regards to d theta. So we need to somehow, the derivative of x is just going to be the derivative of tangent, which is going to be secant squared theta d theta, right? If we took the derivative of x with respect to theta, right, of tangent theta, we would get dx d theta equals secant squared theta, and then we just move that d theta over to that side. So we're going to get that our dx is equal to secant squared theta d theta, and we can sub that in for our dx right now, and we're going to get secant squared theta over 1 plus tan squared theta squared. That's our subbed in expression. And if we remember our Pythagorean identities, we'll know that 1 plus tangent squared theta is just equal to secant squared. So this whole expression can be rewritten as d theta. And secant squared theta is just equal to secant to the 4th theta, right? So this can just be secant to the 4th theta, right? And 2 of those secants cancel with 2 of those secants to give us the integral of 1 over secant squared theta d theta. But that 1 over secant squared theta, right, is just equal to cosine squared theta d theta. And so now we're left with this simple integral of cosine squared theta. You should recognize that cosine squared theta, right, because it's an even power, we're going to use our half angle identities and rewrite this as 1 plus cosine 2 theta, 1 plus cosine 2 theta over 2 d theta, just like that. And we can draw out a 1/2, right? And then we can break that up as the integral 1/2, right, just like this. And if you go through the steps, you will find theta half plus sine 2 theta over 4. And this is our final integral in terms of theta. But we need to somehow sub back in our x. And we said that x was equal to tangent theta. So we can say that theta will be equal to arctangent of x, right? And so that first one can just be rewritten as arctan of x over 2. But it's the second one which is a little bit more tricky, right? This sine 2 theta. And the reason it's more tricky is because we don't have a very convenient 2 theta or anything like that. So we have to reinterpret this sine 2 theta as sine theta and cosine theta. And this is just a standard identity, a double angle identity that you should have known. And now we can find the sine of theta. So the sine of theta, if we go back up to our triangle up here, is just going to be equal to, sine of theta is going to be equal to opposite over hypotenuse, or x over the square root of 1 squared plus x squared, which is just 1 plus x squared. And our cosine theta is going to be equal to the adjacent, or 1 over the hypotenuse, which is the square root of 1 plus x squared. So we can rewrite this first expression as 2 times, right, our sine theta, go back up and check, but it's going to be x squared, 1, just like this, times our cosine theta, which we said was 1 over square root of 1 plus x squared, all over 4. plus c. And that's going to be our final integral with respect to x. And you can go back and multiply these through, and you're probably going to get 1 plus x, right? X over 1 plus x squared times 2, so 2x over 1 plus x squared over 4, and simplify that further, right? But the general process that we've gone through is to say that if the expression takes either the form of a squared plus x squared, a squared minus x squared, or x squared minus a squared, that we can use a substitution, right? And depending on the form, one of those three forms, you're going to use a different substitution, right? Then you're going to create this kind of mock-up triangle right here that you can use as reference for theta, and theta is always going to go on the left here, right? If we wanted to, let's say we had x squared minus 16, right? My mock-up triangle, and then I would do a secant substitution, and I would use this triangle as reference for the rest of my problem, right? And then once we've done that kind of triangle, we can do a substitution for x using tangent and simplify our expression. Go through the whole 9 yards, and then once we've got it with respect to theta all solved out, right? And you're going to also have to, derive your x in order to get your dx in terms of theta. Once we've found the integral in terms of theta, we sub back in our x, right? And that requires knowledge of half and double angle identities and the Pythagorean identity to get your final integral, which will be around here.